At exercise 9a, looking to differentiate a variety of different functions, some all of which you've seen before, but definitely it's new stuff. So let's have a look at this. First of all, a couple of starters for you. You're meant to be able to convert these angles, so perhaps you might want to just remind yourselves how to do this. You're going from degrees into radians, so see if you can remember how to do that. Hopefully you've paused it and you've done them, and I'm going to do it. Now the key, of course, is that pi equals 180 degrees. So as soon as you see 90 degrees, you say to yourself, that's half a pi, or pi by 2. It depends how you want to write it. 120 is like 2/3 of 180, so that's like 2/3 of pi. Now 15, how many 15s? I think 12 15s are 180, so this is a 1/12 of pi. 7, now these are a bit, I suppose the way to think about this is, when you had 15 degrees, you did 15 over 180 and you simplified, and that gave us a 1/12, and therefore it was a 1/12 of pi. So here I suppose it's 7 over 180 pi, and the last one is by definition a over 180 pi. Let's see the answers. There you go. Next starter is linked to logarithms initially. It says write this log of 3x to the 4 in the form of this. So you should be able to recall that there's a rule that says you can split this. So number one, I shall do down here, I shall write log, not sure where it's going to go, it doesn't come up anywhere, so I'll just have to do it. It's the log of 3. When you split a times, it becomes an add. So it becomes log of x to the 4. And the second rule says you can move that to the front. So I think this is log 3, that's the a, plus 4 log x. And obviously the b is 4. The a is log 3, the b is 4. Question 2 is differentiate. Now you can't differentiate this in its present form until you multiply out the brackets. So let's multiply out the brackets. I get 3x squared. Now the 3 over 3 disappears, but I've got a 2, oh, and the x over x disappears as well. So it's just plus 2. Now I do these two, so that's 1 over x times x. Well, that's actually just the minus 1, because the x is cancelled. And then the 2, so this gives me minus 2/3. And the x squares are on the bottom, so I'm just going to make it easier for myself and do that. I shall tidy up, and I reckon it's 3x squared plus 1 minus 2/3 x squared. I think that's right. I'm not going to check it. I think that's right. So when I differentiate, you remember what you do when you differentiate is you pull the power to the front by multiplication, so it becomes 6x, and then you lose the power. Now it's 2 already, so it just becomes 6x to the 1. I'm not going to bother writing the 1. If I differentiate a number, like on its own, it just disappears. This one doesn't though. This is a bit more interesting. Now that should have been to the minus 2, I think. I just spotted that that was a mistake there. I did say that it was on the bottom, and therefore it should be x to the minus 2. So when I do this, I pull the minus 2 to the front and I times. Now minus 2/3 times minus 2 is plus 4/3. I then lose a power. Now if I lose a power from x minus 2 goes to x minus 3. So there you are. Hopefully I did those right. Now some rules then. If we differentiate trig functions, first of all, x, the angle, has to be in radians. That's why I mentioned radians at the start. If it's in degrees, you can't do what we're about to do. So degrees is a no. You can only differentiate and integrate in radians. And we have two rules. The first rule that I want to show you is that if you look at the sine curve, now the sine curve, you'll notice, has a positive gradient initially, and so we can show this on the graph there. That's the positive gradient. In actual fact, it has a gradient of 1. If you look at it, it goes perfect diagonal. When you get to the top here, the gradient is, I know it goes up to 1 here, but actually the gradient here is straight across. So that means it's got a gradient of 0. So that's why I've plotted this blue line, and this blue line is meant to be the gradient graph. And so here you can see the gradient is now negative, it's going down, it's actually the perfect diagonal again, and that's why I've plotted it there. And you'll notice this curve, and this point here by the way, is 1 again, Can we see? Yeah, that's there. And the point I missed out was down here, which has got an exactly 0 gradient again. So that's there. And you'll notice the curve which goes through it is this blue line, and it is actually the graph of y equals cos of x. So effectively it says if I differentiate sine x, I get cos x. That's not an obvious rule, but that's the rule. You can do a similar thing with cos x. If you look at the gradient of this, here for instance it's 0. Here it is -1. Down here it is 0 again. And you can see what's happening. I end up with this blue line, and this blue line turns out to be negative sine x. That doesn't quite show up on the screen, but you get the idea. If I start with cos x, dy by dx is minus sine x. Now it's not obvious that there should be a minus there, but turns out it is important. So summarising this then, this is what you should be writing down in your books. If y equals sine x, you get cos x when you differentiate. When y equals cos x, you get minus sine x. And I think this is best summarised by looking at this graphic. This graphic shows sine going to cos, minus sine, minus cos as you go down. So depending on which one you start with, if I was to differentiate cos, I will get minus sine. If I differentiate the minus sine, I get minus cos. Obviously when you get to the bottom there's nowhere left to go, so effectively I've got to go all the way back up to the top again. And it shows you then, and knowing in lessons I would expect you to write, as soon as you get into a question like this, you write s, c, minus s, minus c, because this is the way we can learn quite easily what happens when we differentiate these functions. And as I said, when you get to the top, you go, get to the bottom, you go back up to the top. So let's now look at what happens when we differentiate tan x, and it's a straightforward. Now this is a reciprocal function which we saw in year 12, and I'm going to look at a reciprocal function soon in year 13 again, but for now just remember that to get sec x, it's actually 1 divided by cos. Now to be honest, at this stage it doesn't really matter. You just need to know that if you start with y equals tan x and you differentiate, you get sec squared x. Now remember that means sec x times by sec x. That's what sec squared means. Or better perhaps written with sec x in a bracket square, but no one ever writes the brackets, they just write it like this. Exponential graphs have also got their own little quirk, and this is the great thing about the gradient of an exponential function is the same as the gradient of the original function, or the so if I start with y equals e to the x, I thought I'd have drawn it, I haven't. So this is the graph of y equals e to the x. Now you can see the gradient of this graph is quite little. So if I was to try to find, a bit like I did with the sine and cos, it'd be quite little over here. So the gradient of this is quite low. You can see it's there it is. Now the gradient here is, well, you could say it's a little bit bigger, but it's not much bigger. By the time I get over here, it's much steeper. So, but you can see the shape of this thing. All exponential graphs work in this way. There is one graph which is just ends up giving you a perfect curve, because you end up with dy by dx equals the same, and that graph has this weird number e because it's a weird number that gives you it. So here's a rule: y equals e to the x, and dy by dx is also e to the x. If I differentiate log of x, my rule is that I get 1 over x. Again, there are ways to show you this. It's probably easier to think of it as the reverse of this, and I will come back to that when we look at integration. So on that basis, hopefully you've written down all those rules. They're all important. Let's do a few. So it says differentiate these functions. So the first one says 0.1 e to the x. Well, I know that e to the x, when I differentiate it, gives me e to the x. Now it's got 0.1 in the front, so it's going to be 0.1 e to the x. If I differentiate 2e to the x, well, it's still 2e to the x. E to the x stays the same when I differentiate it. if I differentiate sine x, now I've again sine, cos, minus cos. That's useful. So sine will go to cos. So this answer is 3 cos x. Cos x over 2. Well, cos x over 2 I suppose is better written as a half cos x. What does cos go to? Cos goes to minus sine. So this goes to minus a half sine. You'll notice the number I'm timesing by just stays the same. 2 tan x. Now if you remember, tan went to sec squared. So this becomes 2 sec squared x. Log, you'll remember log goes to 1 over x. So this is 5 log x, so this is 5 over x. And the one you can't quite see here says a quarter of log x. A quarter of log x, now log goes to 1 over x. So this must be a quarter of 1 over x, which equals 1 over 4x. Here's some more. E to the x minus 2. Now look, if I get x minus 2 here, effectively, I can think of this as, I mean, this says rewrite. I can just think that it to myself as this becomes e to the x minus 2. It doesn't change. It would change if it was e to the 3x or something like this, and there's a multiplication. And what you're meant to do is differentiate the top. So if it was e to the 3x, I'd differentiate this power 3x and I get 3. And so this would become 3e to the 3x. Now when I differentiate the x minus 2, I get 1. So it's just 1e to the x minus 2, which is still e to the x minus 2. This one might be a little trickier to get your head around, and I suppose this is why this is saying you can rewrite this, because when you have something like this where you've got a plus or minus here, you can rewrite this as a times by e to the minus 2, and this is just a number. When I differentiate this, it stays the same. This stays the same. So you can see I can then rejoin them back together again. But you can split them. That's what I'm getting at. So likewise, this one is e cubed times e to the log x. And the weird thing about e to the log x is they cancel and it equals x just for this. Oh, and the e cubed. E cubed is just a number. So my answer on this is actually e cubed, because this is if I'd had, say, 5x and I said differentiate it, you go, that's 5. So e cubed x is just e cubed. What's this next one? 3. Well, look, there's 2 parts to this. I've got to do that. I've got to rewrite that. So I'm going to write 3 sine over cos. You should remember is tan. 3 over 2 tan x. 4 over 2 is 2. Cos over cos is 1, so it's just that. Now, well, I know that tan becomes sec squared, so this is 3 over 2 sec squared x, and the 2 disappears. Log x over 6, again, probably best to think of that as a sixth of log x, and therefore it's 1 over 6 times 1 over x, which is 1 over 6x. Log of x squared. Well, again, you should recall that you can bring the 2 to the front. It's like 2 log x. That's the power law. So when I do that, that's the same as 2 times 1 over x, or simply 2 over x. It's very similar to this one, I suppose, over here. And the last one, log of 3x. Now when you have a log of these two things multiplied by each other, you can write this as log of 3 plus log of x. So when I differentiate log of 3, that gives me nothing, it's just a number, plus log of x gives me 1 over it. So this is what we're going on to now. We're going to look at in class exercise 9a. We've got more to do, so we'll hack through a few more examples when we get into class, but that's essentially where we're moving towards. So hopefully that makes sense.